In this lecture, I will discuss about the orthogonality theorem for irreducible representation, and the content of the lecture is from the textbook of Mathematical Methods for Physics and Engineering by Rayleigh, Hobson and Benz. Now, we have already discussed about the reducible representation and irreducible representation in the earlier lecture, and for the group G, that is, if we consider the symmetry elements for an equilateral triangle which are isomorphic to the six set of matrices, as well as a permutation group which we have discussed in our earlier lectures. So we have constructed a particular table showing that there are three different types of irreducible representation, A1, A2 and E, where I, A, B, C, D, E are the six elements. Now for this particular table, we will show a particular theorem which is known as the orthogonality theorem. Now this particular theorem states that in a certain sense the irreducible representations of a group G are as orthogonal as possible, which is given as follows, and that is for each if for each irreducible representations the elements in any one position in each of the G matrices are used to make up a G component column matrices, then any two such column matrices coming from different irreducible representations are orthogonal, and any two such column matrices coming from different positions in the matrices of the same irreducible representation are orthogonal. So this is the basic theorem, and if we represent this theorem mathematically, so it will look like this. But before that, I have to say that apart from these two particular statement, this orthogonality is in addition to the irreducible representation being in the form of orthogonal matrices. We have already discussed, that is, the elements of this particular group of six elements, they consist six unitary matrices. We have already discussed about that, and these matrices, for these matrices, the rows and columns are mutually orthogonal. So this is in addition to the requirement of these two particular criteria. Now if we represent these two particular criteria mathematically, so this will look like this. That is, suppose if we denote the entry in the ith row and jth column of a matrix Dx. So you consider a particular matrix representation Dx, and for a particular element you are denoting as Dx ij, where I is the row and j is the column, and d lambda, d cap lambda and d cap mu are two different irreducible representation of G having the dimensions n lambda and n mu respectively. So just sometimes before I have shown you a table in which we have prepared the three irreducible representation for the group G, A1, A2 and D. So three different irreducible representations are there. Now you just take any two of them, and suppose they are d cap lambda and d cap mu. So if we consider the product of these two irreducible representation, then this product can be written in this particular format. You just look at the left hand side of this equation. So we are multiplying two matrices, and we are writing in this way, that is d cap lambda x ij, that is element for to denote a particular element we are writing ij, and we have taken the complex conjugate of its values, and this is d cap mu x kl. So kl is particular index which is denoting a particular element, and we are considering the product of them, and the right hand side is g by l lambda and delta ik, delta jl, delta lambda mu. So right hand side has been written in terms of the Kronecker and delta function. Now in the earlier examples we have considered only real matrices. So if we would consider some imaginary matrices, then there we have to take the complex conjugate, but here and there is no meaning of the complex conjugate for the real matrix elements. and in the right side it is clear that there are some Kronecker delta function, and we know about its properties. So the right hand side has value 1 if its two subscripts are equal, and has the value 0 otherwise. Thus the right hand side is only 0 if I is equal to k. You see the indexes, if I is equal to k, j is equal to l, and lambda is equal to mu, all at the same time. So that should be satisfied all at the same time. In that case only right side will give you some values, otherwise the right side will be 0. Secondly, the summation over the group elements x. You take you see that in the left hand side the summation is over the group elements x. It means that g contributions have to be added together, as there are total 6 elements and small g is the order of the group. So value of the small g is 6 here. So you have to consider the g contributions, you have to add them, and each contribution being in a product form. You see that this is in a product form, product between the two irreducible representation, product of entries drawn from the representative matrices in the two irreducible representation d cap lambda and d cap mu respectively. The g contributions arise as x runs over g elements of g, as there are total g elements, so there will be total small g contributions. Now this summation, that is right side, will produce 0 if either the matrix elements are not taken from exactly the same position in every matrix. That is, you have to make the index I is equal to j, I is equal to k, and j is equal to l. So if it is not so if it is not, that is I is not equal to k and j is not equal to n, then definitely the right side will be 0. And similarly, so they should if they are different irreducible representation, that is if lambda is not equal to mu, then also the right hand side is 0. So right side will give you values only when I is equal to k, j is equal to l, and lambda is equal to mu. In this case only the right side will give you value, otherwise the right hand side will be 0. Now whatever we have stated, now we will demonstrate with some example, then it will be clear, that is what is the meaning of the orthogonality theorem. Now suppose we have taken ijkl is equal to 1, that means all indexes we are taking same, but we are considering different representation, that is one is a1 and another is a2. Okay, now you just see the character table again, then it will be more clear. So one is a1 representation and another is a2 representation, and indexes are same. So in the orthogonality theorem, the left hand side is actually the product between the elements. So these are only 1 by 1 matrices, so only product between the elements will be like this. Suppose if you consider this particular column, then product will be 1 into 1, then again 1 into 1, then again 1 into 1, then 1 into minus 1, then 1 into minus 1, then 1 into minus 1, and you have to sum over this product. So what I have stated is this. So if you consider the sum of these products, so that will be 0. Now it should be expected. Why it is 0? Because lambda is not equal to mu, that is why the this 0 value is expected. Now suppose we are taking ij as 1 2 and kl as 2 2, that is we are considering different elements, but representation is same. Suppose d lambda and d mu is equal to e. Now ij is 1 2 and kl is 2 2. That means suppose you again see the representation. So this is the E means this set of matrices, and you have to find the product between 1 2 element and 2 2 element. So what is 1 2 element? That means row 1 and column 2. For example, for first matrix, this is the 1 2 element. And what is 2 2 element? So this is the 2 2 element. So 1 2 you have to find product between the 1 2 element and 2 2 element for each of the matrices. So there are 6 matrices, and what you have to do, you just consider the product between the 1 2 element and 2 2 element. So for 6 set of matrices you will find the product like this. For example, for the first matrix it is 0 into 1, and for all other matrices, and the product will be as given by this equation, and you have to consider the sum of all the products, and it will give you 0. Why it will give you 0? Because you see that you have considered indexes in this way, that is 1 2 and 2 2, but to give you some values all should be same, that is why 0 value is expected. Now suppose in the next case what we are doing, that is we are considering indexes as same, that is ij as 1 2, kl also as 1 2, and lambda is also equal to mu. Then you just find the product between 1 2 and 1 2. I have already denoted what do you mean by 1 2 element. So you just find the product for each of the matrices and add them up, then it will give you the value 6 by 2. So you are getting some values here. And suppose if all the indexes are 1, but d lambda and d mu, they are also either a1 or a2. That is just like this case. In this case we have considered that as e, and here we are considering that as either a1 or a2. Then in this case also we will get some values, and if you add them, the total will be 6. The total will be 6, which is as predicted by the right side of the equation, because g is equal to 6 here. You see the right side here 6 by 2, and here it is 6. Now you see the equation, that is g by n lambda. So in the case of E, n lambda means dimension of the matrix is 2. So g by 2 means 6 by 2, and for the a1 or a2, a lambda is 1, so g by 1 means 6 by 1 is equal to 6. So right side holds in these cases. So this is what about the orthogonality theorem. So I hope you have understood this lecture, and for further understanding I request you to go through the textbook of mathematical methods for physics and engineering by Riley, Hobson and Benz, and I thank you for listening my lecture.